So our next speaker is Nils. Nils was a PhD student in the maths in the School of Mathematics until about 6 months ago. Is that right? Maybe slightly longer. Yeah. And he's now a postdoc at Exeter. And Nils is going to. I forgot my pen. No, perhaps not. Okay. So Nils is going to tell us about hydrodynamical simulations of mixed modes in evolved low mass stars.
Thank you very much. I'm not going to start with this talk. I would like to thank the organizers for giving me this opportunity to speak here, but I guess more so for instituting the Sam Myers Memorial Lecture, because Sam was a very close friend of mine, and it just means a great deal to me that this lecture was instituted, and I would like to say a few words about my friend Sam, if that's okay with you. Because I just miss him dearly. Sam was, I think, one of the most unique people I've ever met. And I just admired the way that he looked at the world. Because there was a time when Sam went climbing in Wales, and he was on a very large cliff, and he fell a few meters, and he injured his ankle. And he came back in the big boot, and understandably, everybody was very worried, because of course you would be. He just fell off a cliff for a few meters. And then I asked him, well, weren't you terrified? It must have been terrifying. And he answered, no, new experience. And that's just the most wonderful way I've ever seen of looking at the world. And it also highlights who Sam was as a person, being someone that is both very curious to learn about the world, to gain new experiences, and also incredibly quick-witted. Sam had, as Steve already said, a genuine interest in most everything, as far as I could tell. Maths and science, of course. Sports as well, where he was better than me in every sport I've ever seen him do. That doesn't say much. He was actually very good at sports. He was also very good at music. I sadly did not get to enjoy this at any point. But, you know, Sam and I, we sat next to each other in the office, which is why, you know, I've shared quite a deal with him. I've spoken to him a lot, we chatted a lot, we talked about work a lot, and it was just wonderful to do, to sit next to him and to get to know Sam. Most important of all, I think Sam was a good friend, which is all you really want in a person, at least to me. Sam was there when you needed him. Sam even checked up on me when I wasn't in the office for some reason, which usually was that I was ill. And Sam could just cheer you up with a quick joke at any time. When I was stressing about going for my APR, my annual progress review, with Steve, actually, I wasn't stressed about Steve. I want to make that clear. But I was just stressing because of that's who I am. I stress for these sorts of things. He said, well, you shouldn't worry about all that. You should just ask him to explain the offside rule to you. That'll be enough. So even though I've known Sam for too short a time, I think he has made quite a strong impression on me. Just the way he looked at the world was wonderful, and he was just so kind to people. I'm sure I will continue to miss Sam for the rest of my life. Which now puts me in a little bit of an odd position, considering that I have a talk to give. And every time that I thought about what I wanted to say and what I was writing down, what I wanted to say, I kind of got stuck at this point because I don't know how you really go from here. So what I'm going to do is I'm going to act like I'm back at my desk with Sam next to me, talking about work with him, you know, what happens to old friends when they meet again and immediately fall back into old habits. So this talk's for you, Sam. I hope you enjoy. Right. Mixed modes in a low mass star. I'm sorry, I can't do this transition properly. It's very hard. What's the button? There we go. This is preliminary work that I've been doing in my postdoc in Exeter. I've been there for 6 months now. I work with Isabelle Boaf and Thomas Guillet. It's a lot more astrophysical than what I used to do. But I hope to convince you it's still very interesting, still very fluid dynamical. The motivation lies in evolved stars, specifically subgiants and red giants, which are stars that have exhausted their hydrogen in the core and are now burning hydrogen in the shell. As a result, their cores are contracting and their envelopes are expanding. And by conservation of angular momentum, if you have no exchange, their cores must spin up, like a ballerina retracting the arms, and their envelopes must spin down. And this is what we see. You can actually measure this. Well, okay, you can get mixed modes to measure this, which happen to be sensitive to this small area. And then you can look at the surface, where you can actually see these mixed modes. The bit in between, don't really know how they got that. Still, you can measure the core rotation rate and clearly see that the rotation rate here is about a factor of 4 higher than it is over here. And we can clearly measure that indeed we find a differential rotation using mixed modes, which is very interesting considering that we can't find what the core rotation rate is for the sun. And if you then start looking at populations of these, then you find that there is actually a rather weak increase of the core rotation rate with age during the subgiant phase, which is a bit odd. You'd expect a strong increase. So there's some sort of mechanism that's transporting angular momentum from the core to the envelope. Equally, if you start looking at the red giant phase, the red giant branch, you actually see a decrease of the core rotation rate with age, which you can see over here. This is now the rotation period, so up rotation period. If the rotation period goes up, rotation rate goes down. Age and radius are related, so as you expand, you see this small trend towards higher and higher core rotation rates, and then you get, this is the helium burning phase, you get the same, some sort of jump where it even slows down further. So there is some mechanism in there, many options, that transports angular momentum, and one of the ideas is maybe it's the mixed modes themselves, which we use to probe this differential rotation observationally, that are actually responsible for these for this angular momentum transport. The catch of this all is no one's managed to simulate a mixed mode yet. So we don't actually know that much about their properties and what they're like. We have some asymptotic ideas and we have some approximations, but we don't have actual simulations. And that will be the aim of this talk, essentially. But before I get into showing you mixed modes, let's take a look at what are modes. A mode is just a standing wave. Considering that stars are usually quite spherical, they are represented by some radial profile and then some spherical harmonics. The radial profile is defined by its radial order n, and the spherical harmonics then tell you about how it works on the surface, essentially, on surfaces, with angular degree L and azimuthal order m. The rest of this talk, or at least the simulations, are going to be 2D, so we can forget about this part. And the types of mode that are of interest are acoustic modes with a radial order NP, or P modes, hence the P. And this NP is positive, and gravity modes with a NG, or G modes, with a radial order that is by convention negative. And notice I haven't said mixed modes out of these two, because mixed modes is just a mix of those two. Now those acoustic modes and the gravity modes, they originate from sound waves, which everybody in this auditorium is pretty familiar with, considering I'm using them now, which are restored by pressure. And what's most important for them in this specific talk is that they have a minimum frequency, which is given by the Lamb frequency, which depends on the L of the specific mode. The gravity modes, which come from internal gravity waves, which are traveling waves, but then they form the standing mode, are restored by buoyancy force. The idea being that we have a density partial with a certain density rho naught, We displace it. It is now heavier than its surroundings, so it will start moving downwards, lighter than its surroundings, go back up, and then we get wave motions. What's most important here is that the maximum frequency for these is given by the buoyancy frequency n. So we have a minimum frequency on a sound wave, maximum frequency on the G modes. And the mixed modes are nothing more than a coupling of P and G modes to create a mode that has both of these characters. So we're going to pick a red giant model, because that's where the mixed modes are interesting for angular momentum transport potentially. It's defined as M1 in this particular paper. And this is now a 1D, comes from a 1D stellar evolution model, which tells us the profiles of N in blue and the Lamb frequency for LS1 in orange and for LS20 in green. This dashed part of blue is where the buoyancy frequency is negative. We will have no G modes here. The idea is then that you find two wave cavities. You find wave cavity 1 below, because it's a maximum frequency, the N for the G modes. You find waves, G modes below the blue line, solid blue line, and you find P modes above the orange line if they have LS1, or above the green line if they have LS20. So for most of this regime, what you will notice is that you will get either a acoustic mode up here, happily traveling up and down, or a G mode down here, happily traveling up and down. In this particular regime of frequencies, you can see that we can get a G mode, which can then go through a region where it can't exist and hit onto a region where there is P modes. It will couple with it and travel all the way out, and then travel all the way back, go through the region where it can't exist, this evanescent region, and come back. This is how these G modes are made. They go through this coupling region where they can't exist, and then essentially get married together. So we're going to use music. That's the code developed in Exeter. To simulate this, we will model 2D, fully compressible Navier-Stokes. We have no rotation or magnetic fields because, as I've said, this hasn't been simulated before, and I'm not going to make it more complicated for myself right at the start. We're going to solve for density using the continuity equation, momentum equation, and the internal energy. We'll get pressure and temperature from the equation of state tables, which are specifically the opal tables. We will use the 1D model that I've shown you, blow it up to a 2D model. We will get a meridional wedge slice. What that means is we will take the star from 2% to 90%. We use meridional, so it's from north to south pole essentially. And we use a wedge. We cut off the lower 15 degrees on both sides. Our boundary conditions are impenetrable at the inner and outer radial edge, and they are periodic at the meridional boundaries. We let the simulation run until it hits steady state, as you can see here, well, statistically steady state. And then in this latter part between the two solid lines is where we will take a spectrum later on. Great. 1 second. I guess I have something. I guess I will just show you the video of the flow while I fix this. So what we see here is on the left, the radial velocity. In the middle, we see the horizontal or meridional velocity. And on the right, we see the temperature perturbation with respect to a reference state. We get, as expected from our model, we have a large convective region with a lot of convective eddies rolling around, and then a small radiative region where you can see essentially the standing G modes, but you have to have very good eyes. Now, of course, these flows aren't really going to tell us too much about the modes themselves, except that you can sometimes see some internal gravity waves actually emerge over here, which is not actually related to the talk. I think it's just cool. You can see here when an eddy hits onto the boundary, you get these beautiful, almost beam-like features here and here, which is the internal gravity waves being launched from this boundary. Now, instead of looking at the flow, we will look at a spectrum, multiple spectra, to actually identify the modes that we have in our system. We will take a wedge harmonic transform, because we use a wedge, to transform all of the meridional, the horizontal components, to angular degrees. And then we will take an FFT to get a frequency space. We will not touch the radial direction. So what we end up with is a data cube at all L's with spectra of frequencies of the waves and then at a given radius. So this is at L is 0. At L is 0 there is no G modes, there is only P modes, and therefore there's also no mixed modes. These modes are harder to see than I hoped they would be, but you can sort of see them go up here all the way through 1 mode, 2 mode, 3 mode, 4 mode. And they are all roughly equally spaced as is predicted for these P modes. Down here in red, we have used an eigenvalue solver using Daedalus to get theoretical predictions of where the modes are and what they look like. And as you can see, for the very high frequencies over here, these modes line up quite well. For the lower frequencies, Daedalus, this eigenvalue solver struggles a little bit, so we have some improving to do. Like I said, preliminary results. If we then go up to a higher L, this L is now fractional because we are using a wedge transform. We see a whole host more modes, most visible, I guess, from the actual theoretical predicted modes. Down here, we see a whole scala of G modes very close together. And then over here, in orange, we start seeing actual mixed modes, which are now modes with P character over here, and then G character over here. The lines are as before, so this is the buoyancy frequency curve, so you can only have G modes below this blue line, and the orange curve is again a Lamb frequency curve. You can only have sound waves or acoustic modes above this line. But as you can see, here and here and here and here, they couple through this specific region. Another point of note is you have here a region where there's now 2 points where they have to couple through, which means all the modes over here are messy, and they will look messy as well. I just thought I'd let you know beforehand. The modes themselves are good. They need a small frequency shift to actually line up. But if you do that manually, which was quite a bit of work, then you can get this beautiful agreement, starting off with just the P mode. I picked the P mode, the highest frequency P mode, radial order of 16, so 16 nodes going all the way through. In black is our music prediction, and the colored is our in black is our music simulation, colored is our Daedalus prediction. Again, this is at L is 0, it's just a P mode, so we have no G mode part. So we see this part is all the way through P mode, and then there's a small evanescent region. This is from the radial velocity spectrum. That is cleaner. There's a rather large-scale flow going through the model in the meridional direction, which then, as you can see, produces quite a bit of noise. So we tend to look at the radial modes and then check if they're correct, and then flip to the full velocity power spectrum. Still, you can see, even if we have this noise, you can see that it agrees quite well here in the radiative zone, where there's no convective noise, and at the very end, where the convective noise is weak. Next up is a G mode. We have lost the blue part now because there's no P mode part here. We just have a G mode part in the radiative region, which then, the moment it becomes convective, becomes evanescent. The agreement is very nice here, if I would say so myself. And then in the convective region, I don't know how well the agreement is. The convection is just in the way of seeing things. But we can again flip into the full power spectrum. Again, see very nice agreement in the radiative region and get confused about what's happening here. Still, based on this, I think the agreement is good, and we are actually accurately capturing G modes. So we have P modes accurately, we have G modes accurately. Do we have mixed mode accurately? Yes, we do. So this is a mixed mode. It is at a frequency of 380 microhertz, 15-minute period or so. But as you can see, the music mode in the background lines up perfectly with our prediction, except maybe here. So we can just indeed simulate these mixed modes. We have them. Like, this is, no one else has done this before, but it works. We can get them, and we can start making statements about their amplitudes and their kinetic energies, which I just think is very cool that you can just do this. Switching into the full velocity spectrum again, the convective region is hard to measure, but the radiative zone is bang on, and the very upper part of the convective region is bang on. To illustrate then how many modes we have, I've just done the first 5 L's because I thought I'd spare you your senses. In blue, we have the P modes going over here. And then the higher G modes and mixed modes are in orange, green, red, and purple. Over here, these are the pure G modes at a very high kinetic energy. Over here are the mixed modes. This is the region where you have that double coupling region, so the agreement isn't as good, which is highlighted by some of the massive error bars on these, which just indicate how good or how bad the agreement is between our theoretical prediction and the music spectrum. This rapid decay, or this rapid fall-off in energy is most likely linked, I think, to the convective energy just falling off with frequency quite rapidly. But we see that these mixed modes, even at these very high frequencies, where they're not really efficiently being driven by convection, have very nice, stable kinetic energies. That's it, essentially. Again, this is preliminary results. I was just wanting to show you that we are able to capture P modes, we are able to capture G modes, and we are able to capture, as never before, mixed modes. So the next steps here are we want to constrain the angular momentum transport that comes from these mixed modes and analyze them in different types of stars, different evolutionary stages. Is it true that they are efficient for red giants to transport the angular momentum? Is it true that they are inefficient for subgiants? All these kinds of questions is what we are looking at now, but for now, it's more of a show you, hey, we've got the technology, we can do this, we've got the mixed modes, and I hope to produce a lot of very interesting results from this. I will leave you with a video of scrolling through all of those modes and then end it there.